Good day, everyone. In this video, I'm going to discuss the closure of a set that can be completely described in terms of its limit points. Now consider here Theorem 5.6. So we have here A, a subset of a topological space X. Then a closure of A can be written as the union of the set A and its accumulation point. So it can be written as this. So to illustrate this theorem, we use the previous example, example 3.1, wherein we consider here X, set X, and we have here the topology. Okay. So we let A be equal to this set BD. And then we have already shown this one, the closure of this set is in our previous video, the closure of BD is equal to the set with elements B, C, D, E. Okay, so we're done showing this one in our previous video. So here, a point P in X is called a closure point or adherent point of A if and only if P belongs to the closure of A. Now in this case, since this is the closure of A, therefore point B here, point B is a closure point, or shall we say adherent point. Also, C is in the closure, therefore C is a closure point. So we do have here 4 closure points for set A. So B, C, D, and E. Okay, here, let's get first the derived set of A. So I will be showing you the concept. Why is it that the closure of A is equal to the union of A and its accumulation points, the set of accumulation points or the derived set. Now recall that P is an accumulation point or the limit point of A if and only if G is open containing P, then we have this inequality. The negated neighborhood here is intersection with A is not empty. So let's do this. We note here that for the accumulation point, P is the point in X. So it means we will be testing all the elements of X for the limit point of A. Now let's start first when P is equal to A. So to show that A is a limit point or not, so we use this. So to show that if it is a limit point, this must be satisfied. So we will get open sets containing A. So open sets containing A are, we have open sets containing A. We have, so these are all open sets here, members of the topology. Open sets containing A, we have first X contains A. Next, the set, this one. Next, we have this one. So we only have here 3 open sets containing A. Now notice that if we are going to consider this is our G, actually this is all our G, open sets containing A. So if we will consider this Then we subtract it, this set, with intersection. We have intersection A is BD. Now, what do you think is the answer? Now, notice here that this is empty, right? It is empty. Intersection with this is, of course, empty. So, this is not satisfied. We can say that A is not a limit point of the set A. Now, let's test for B. When P is equal to B, so the open sets containing B. Oh, by the way, this is containing A. Excuse me for a while. This is containing A. Okay? Containing point. Containing rather point A. Okay. So, open sets containing point B, of course, we have X. Then, what else? We have this set. We have B, C, D, E. And then, we are going to show this one. Now, notice if we have X minus this set, intersection A is this set. The intersection is X minus B is ACDE. So, ACDE, so it means the intersection is D, point D. So, it is not empty. Another one here, if we have B, C, D, E, minus set B, intersection with BD. So, if we remove here B, still we have the intersection set D. So, this is not empty. So, it is satisfied for all open sets containing B. So, we can say that B is a limit point of A. Follow? So, let's try for, okay, take note here that A, by the way, this is the derivative of A, right? So, A is not in here. We have B. So, let's try for C. Now, let me erase this one. Okay. Now, for when P is equal to C, we have open sets containing C. We have X. We have CD. We have ACD. And we have BCDE here. So, if we subtract, if we have here X minus C, then intersection with A, we have BD. So, minusan na to si C, we have ABDE. So, common is the set BD, it is not empty. Now, for this, for CD, take note, if we subtract, if we negate set C, we are left with set D. Intersection it with this, so still not empty. Another one here, negate C, we have AD, intersection with this, so we have D, so not empty also. And then here, we have C, so BDE, still very common BD, so not empty. So all are satisfied, all open sets containing C. Therefore, we can say that C is in the limit, is the limit point of A. So C belongs here. Another one, when P is equal to D, when P is equal to D, open sets are X. We have CD. We have also ACD. And we have BCDE. Now, notice that if we are going to get this as our G, we have CD minus D. And then we are going to get the intersection with A. A is BD. So, remove D here. We are left with set C, intersection. So, this is empty. So, this is not satisfied. Therefore, D is not a limit point of A. So D does not belong here. Now, when P is equal to, the last one is E, open sets containing E, we have X, and we only have B, C, D. Okay. And the same process, we can say that E is a limit point of A. Hence, the derived set of A is this set. Okay? Now, A union, the derived set of A is equal to the set BD union this one. So we have B, C, E. This is equal to the set B, C, D, E. And notice that they are equal, which is equal to the closure of A. So we have illustrated already that the closure of A is equal to the union of A and the derived set of A. So in view of Theorem 5.6, if P is a closure point of A, so if P is a closure point of A, if and only if P is in A or P is in the limit point of A, because we have here union. So take note here, D is in A, but not in the limit derived set. It is not a limit point. It is in the set A. So that's why it's or. It could be in A or in the derived set of A, or it is a limit point of A. Now let's have here another example. Let us try to consider the set of rational numbers. Now I discussed this already, that the limit point, that every real number is a limit point of Q. Hence, the closure of Q is the entire set of real number, because the limit point is the real number. And we know that the closure is a set Q union the limit point. We have the derived set rather of R is, of Q rather, is R. So we have here, Q na to is, A na to is Q. Then, of course, this is equal to the union of the derived set. We know that the derived set of Q is equal to R. We have shown that already. So this is equal to R. Hence, the derived set of Q is equal to the set of real numbers. Okay, so I illustrated already Theorem 5.6. Now, in my next video, I'm going to discuss there another concept, what we called dense, wherein it has, we can use this example for our next topic. Okay, that's all for now.